Are we recording? Yeah, we are recording. Okay, great. So hello all and welcome to the week 7 of this Intro to Machine Learning PMRF TA lectures. So before we go ahead with the assignment 6 questions, I think there are some questions on the chat that we want to solve first. So let's go ahead. This was one question that somebody posted just now. Um, Okay, so we have a neural network which can be considered as multiple simple equations stacked together. Okay, suppose you want to replicate the following function. So we have this complex function. It sort of looks like your XOR sort of the function, right? Which cannot be solved by a single boundary. But we have two simple inputs. So H1, H2 are two simple functions. Again, linear functions. So how will do your so what will the final equation that you would want to use to replicate this complex function with these two simple functions? So any thoughts? I mean, I think Varun, you were the one who put it across. So any thoughts? What seems like it? Go ahead.
Yes, sir. No, I had doubts like how to solve this.
See, what it feels like is it feels like an XOR. So hopefully we can try something like this. XOR is what, right? So it's AB bar plus B A bar B. So this one something. You might want to try this one first. So if you see, actually let me just put all of this in the PDF. So do I do this? One second. Let me just put this here. So. So this is one simple inputs, and then here is it. And then we have these three as the options. So again, from intuition, I think the third one is what seems like it because it seems like an XOR problem. So let's see, what comes out. Uh,
No.
okay, I hope this is visible, right? Okay, so just see. I'm sorry, who is?
No.
Yeah, thank you. Yeah, so if you see here, let's say, see, the more interesting part is, for example, this area, right? Because H1 is saying that this area is positive by H2 also, but we need this area to be negative, right? So let's look at this one. So H1 um, and not H2. So this will be, for this area, this will give me +1 and not this one, right? So let's say this is, so this would be saying it belongs to class plus and not to class 2. Um, so let's say the point is here. So H1 says it is, so this is for this dot point that we have. H1 says it belongs to class, positive, and H2 says it also belongs to class positive account H2. So now what will this say? So that let's say this, we'll call it 1 and positive is 1 and negative is 0. So 1 and not H2, that is not H1 is 0, right? Or then this one, not H1, um, that is 0 and 1, right? So then you get 0 and this becomes 0. So 0 or 0 is 0, which is exactly what you want, right? So this area, so a point in this area seems to be classified as 0 when I take this particular option, right? So now I think you can try for all the remaining ones and see, what is coming out. Is this okay, or do you want me to solve the whole thing?
That's okay, sir. Yeah. So basically, you should solve for each and every combinations.
Yes, yes. See, so again, they've not given
using
it
using XOR gate.
using XOR. So yeah, because again, very roughly, it seems like XOR, and that's what it should be sort of, right? Because it seems like an AND gate or gate, and you're trying to solve whatever. So, but the idea is this. So it seems like an XOR gate, and all of these boundaries are exactly. I mean, hoping that they're the same boundaries, right? That's a fair assumption to make. So now this one partitions your space into four regions. For each of those four regions, how does H1 behave? How does H2 behave? And then you can just look at these different options. That could be one way to solve the
So
problem.
basically, it's like a OR gate, AND gate, and all those you should try. NOT gate. Yeah.
Right, right. That sort of a thing. Yeah.
Okay. Thank you.
That's what my first intuition
Yeah.
suggests. Yeah.
So now,
Is that clear?
yes, sir. And the next one, how many times, sir?
Yeah. One second. So this is chat question one. Okay. Uh, and question two on chat is something which says, okay, how many times do we need to train the SVM model in one versus all method if we have 4, 5, 6 class classification problem or n class classification problem? For example, for 3, it will be 3, for 4, it will be 4 or 6, etc. So does anyone want to answer this question? We have covered this actually sort of question previously also. Anyone wants to take this? So one versus all, we're trying to use one versus all for an n class classification problem, right? And we want to use SVM, right? So how many different SVM models will we have to train? Any thoughts? One. Uh-huh. We have n class classification problem. So how many SVM models will have to train to be able to do this n class classification problem? N number of models, right? So Annapurna, why n number of models? From where did you get the intuition of n?
So for each class, like one model has to be created. It's one versus all. So
One versus,
basically for each class we need, yes, yeah.
right. So one versus all is there in the name. So what you will do is you will take one class versus all, in the sense all the remaining class, right? So what you will do is you'll do one SVM model, you'll train one SVM model to do this classification. So you'll pick one class, let's say C1, let's say you have C1 to Cn classes, right? So C1 against C2 to Cn, all C2 to Cn, right? So this becomes, let's say, positive, this becomes negative. So you will do a binary classification. Again, you will do the one more model saying C2 versus C1 and C3 to Cn and so on, right? So you will do this n number of times. Now, when you get a new sample, you will run through all of them, and whichever has the highest probability of falling into whatever the class, that will get assigned to that class. That's the way you can use SVM for a multi-class classification problem, right? So what is the other approach, by the way? If you don't want to use one versus all model, what's the other approach? Let's just cover that question as part of a similar thing, right? We covered this also, I think, in the last section. Anyone? One versus all is one approach. What could be the other approach?
That probability, like neural network output of n class, which is the highest class, highest probability, we take that.
No, correct. So in case of neural networks, it's a bit simpler. That's I agree. If you want to use SVM, you want to use SVM for an n-class classification problem. So one way to do this n-class classification problem using SVM, which is a binary classifier, is one versus all. What is the other one? SEM is mostly used for two-class problems only, I think. Correct. So Ashutosh, you're correct. SEM is only used for two-class classification problems, right? So, but if you want to use SVM for n-class, one way is doing this, one versus all. What is the other way? So the other way is one versus one, right? But the issue is, in this case, what will happen is you'll have to train NC2 number of models, right? Because you'll say, okay, C1 versus C2, you will train one model. C1 versus C3 also you will train. Again, let's say C2 versus C3, and so on. You'll keep on doing whatever n number of things you get. Then whatever test sample you get, you will run through all of these, and whichever then starts winning. For example, C1 versus C2, C1 wins. Then you will you will check, okay, what was the result of C1 versus C3. If C3 wins, then you will check C3 with with the remaining classes. That's another way of doing it. Okay. So if you want to use SVM for multi-class classification, there are two approaches, generally known two approaches. One is one versus all or one versus one. Okay. So the issue in both have their own issues. In one versus one, you have to train large number of models, right? Because here you have to train n models. Here you have to train NC2 models. But whereas here the one issue is that if you do one versus all, then you will deal with something called as class imbalance problem, right? Because let's say, assuming that all classes have same number of samples in their this in their support, what ends up happening is in this particular SVM, you will have very less examples for this class versus here you'll have lot many examples. So SVM might be biased towards these sort of this particular set of classes. So again, there are ways to try to solve that, and there are different ways people have tried to see how to overcome those things. All right. So Varun, is this clear?
Yes, sir. Thank you.
Okay.
Yes, sir. It's clear.
What kind of precision boundary will we get in case of multi-class classification using SVM? Yeah. So let me ask you back. So let's say you're doing one versus all. So what kind of decision boundaries you will get? How many SVMs you're training? You're training n SVMs. So one SVM gives you how many decision boundaries? One, right? Yeah, so yeah, general SEM you'll get, yeah, linear, right? One linear boundary you will get. So in case of this setting, one versus all, you have n SVMs being trained. So you'll have n decision boundaries. But each of those decision boundaries is doing only one particular task, that is one class versus remaining. So those n decision boundaries, right, will actually what do you say classify your whole instance space, your feature space into n regions, right? In one region C1 will be the best class, in one region C2 will be the best class, and so on. That's how you will do the classification. That's how so these n decision boundaries are classifying your region into n different regions. That's the thought process. Okay. Yeah, so we have NSVMs. That's correct. Sure. Okay. So we'll go to the assignment 6 questions. Uh, all right. Yeah. Okay. So what is an autoencoder? Okay. Does anyone want to answer what is an autoencoder? We discussed this last time. Why this question, Ashutosh? We discussed this last time, no? What is the confusion here? So yeah, I would suggest going back to the recording once. But briefly, what autoencoder means is that you have generally it's a neural network. So where you have, let's say, some input X that is projected generally in a low dimensional space, so as to be able to reconstruct the same input back, right? So X and X hat has to be the same. Okay, we'll move to the assignment 6 questions. Okay, so here we have a sort of a perceptron in question 1 and 2, and they're asking what will be the appropriate weights to represent an AND function and an OR function, right? So So anyone want to answer? How did you, solve this, or any doubts here?
How did we solve? That's what you're asking?
Yeah, yeah. How did you solve this?
Well, I first constructed a truth table for OR, sorry, and then one by one ABCD, I created found out the target function using the weights and see if it match with the truth table. You don't
Right.
have to go all the values, because somewhere at the upper layer itself you see that it is contradicting. So you
Right.
eliminate that, and then the last one, whatever is there, you take.
Right. That's it. Right. Straightforward sort of, solution here. So you can just try all these different weights, and you will end up seeing that here answer B is correct for this particular neural network and this threshold function. And here also for the same threshold function, here your correct weights will be weight number option A. All right. So any doubts on this question? Otherwise, we'll move forward.
Can you explain once? Just see.
Sure, sure. So, okay. Yeah, let me just take the solution here and we can try this exact example. So for AND function, they say that this is what the right answer is. All right. So now what do we want to simulate, right? You want to simulate AND function. So AND function we know, so let's say x0, x1. So if they are both 0, 0, 1, 1, 0, 1, 1, right? As Bhushan was saying, that you need to consider the truth table, right? And what is the true output or what you want, right? So let's say the AND, that is x0 and x1 is going to be this, right? Now, when I use w0 equal to 1, w1 equal to 1, and w2 is minus 1. And they've also said that the bias is set to 1, right? So now you can just see, just pass these through, pass the input through this network for this particular set of weights and see what the output is coming. That's it. And threshold function is set. If it is greater than 0, you will output 1, else you will output 0, right? So you can see if I put 0 and 0 here, I get the sum becomes so 0 into 1, 0, 0 into 1 again 0, and then minus 1 is already there. So it's going to be minus 1, right? So the this sum w0 x0 w1 x1 w2 b1 is going to be minus 1. Minus 1 is less than 0, so the output is going to be 0, right? Or this is called a target in some sense, and this is a prediction, right, of the model. And then 0 1, if you see, you will get this arm becomes 0, this arm becomes 1, this arm is always minus 1. So 1 minus 1 is 0. The threshold function we're using has a strict condition. Only if it is strictly greater than 0, it should be 1, otherwise 0. So 0 is greater than 0 is false, so you'll get 0. Similarly, you will get here, and then this will become 1 because you'll have 2 minus 1, 1, 1 greater than 0 is 1. Right? This way you can solve it, Hariharan. Is that clear?
Yeah. Yes. Thanks.
So basically, just take the inputs and pass it through. Basically, do the feed forward operation. That is, pass it through the network and see what the output is coming. Because we just want to see whether for this given set of weights, is it matching what the target is. The target is function is the AND function. Okay. All right. Same thing you can do with OR function. So same approach. So feel free to give it a try. Yeah. Next, so question number 3, which of the following is nonlinearity to a neural network? Answer should be ReLU function. Gradient doesn't give the nonlinearity to network in any way. Gradient descent is a different method altogether of how to how to improve a solution in an iterable fashion. Bias doesn't give any nonlinearity. ReLU is a nonlinear function, so passing any any value through ReLU is going to give a nonlinearity to the neural network. All right. So any doubts on the fact that ReLU is a nonlinear function? Does anyone have any doubts in that?
No, I don't have a doubt.
Anyone else?
It appears to be linear because when you see it for the first time, you generally don't notice x equal to 0 is equal to 0.
Right.
Therefore, it creates a visual impression of being of linear, though it is non-linear.
Right. It is non-linear. Yeah, correct. True. It is non-linear. Yeah. So if you want to, this is a ReLU function in this way. And for any linear function, if you want to understand what linear, the definition of a linear function is this: f of ax plus b has to be equal to a times f of x plus b for all a, b, and x. All right. In our case, ReLU is defined like this. This is f of x, or let me just not call f.
What is the first equation written? F of ax plus b is equal to a f of x plus b. What is this for?
Yeah, this is the way you define a linear function.
So
So
linear function. Okay. Okay.
Yeah. If a function satisfies this property, then it's a linear function.
Okay.
Right?
Okay. Agreed.
Right. And so ReLU is defined like this, right? So where max of x comma 0. So basically, if you see in the positive region of x, it'll be equal to x, but in the negative region of x, it'll be throughout 0, right? So when you define it like this, and you can so you can see you can try to construct an example where this equation fails for ReLU function. So ReLU will not satisfy this condition, right? Will not satisfy this condition. So try to construct an example where this equation fails for ReLU. Then you can be completely sure that it's not a linear function. All right. One question. So are we supposed to know and, or, nor, XOR, etc. for question like one? Yes, you are supposed to know. More than that, see, even in the week 6 lecture material also, there was a mention of what AND function is, what OR function is, right? So I hope from there, at least, so if you don't know, but at least in that lecture material, it was mentioned. So hopefully, you can use that to get clarity on that biology. Yeah.
How many such functions are there? We have AND, we have OR, we have XOR, we have NOR. Any more? NAND, NAND, which is just the inverse of AND. What else?
XNOR is also there. XNOR.
XNOR is there. Yeah.
NOR is there.
What is X? R? What is R?
What is R? No.
Or is basically addition and AND is like multiplication. Like A and B,
No,
A is 0, B is 1, then 0 plus 1 like that. Like that is OR. And is both should be on. Switch is on. Then it's
what is
like
NOR?
1 and 1.
XNOR?
Not is
What is XNOR?
A is 0, not is 1.
Right. So the basic ones and or that we know. NAND NOR is opposite of whatever and or is. XOR basically is this. It's given as a plus circle B. It's basically AB bar plus A bar B, where A, B are this one. This is just the opposite of XNOR. That is, you take this. A complement of this you'll get in this form. So XOR basically is whenever the two inputs are different, you will get output. That's the way XOR is defined, right? So basically 0, 0, 0, 1, 1, 0, 1, 1. XOR, if you take, you will get here 0, 1, 1, 0. XNOR is opposite of XOR. That's it. So XNOR tests for equality. XOR tests for non-inequality. At least in the binary case. Multiple case, there are different ways to understand this. Is that clear?
Okay.
All right. Question 3. Question 4. Yeah. So suppose you're asked to design a system where you want to perform word prediction. You want to take the output from the previous state, and also the input at each step is to predict the next word. To predict the next word, the inputs at each step of the words for which the next words are to be predicted. Which of the following neural network you will use? So the answer is recurrent neural network. So a few slides that you had in the last about recurrent neural networks is basically it can handle sequences, right? It can handle things which are have a temporal or a sequential order among them. That's generally when we use recurrent neural networks. Convolutional neural networks is basically when you want to use something like which has like a spatial sort of patterns involved in it. So which is generally in case of images, right? Multi-layer perceptron and perceptron are the general use cases which can be applied to any use case. All
Sir,
right.
if the question had an answer like multi-layer perceptron with back propagation, then even that could be the answer to this question, right, sir?
No. So see, so when you say multi-layer perceptron, it means with back propagation only. And by the way, all recurrent neural network, convolutional network, all of them are trained using back propagation only. See here, the idea is that there is some sequential dependence coming into picture. That is what you want. That is what they want to, highlight here. So that sort of a ordering or modeling can be done through recurrent neural networks better than any of the others. That's the
Sir, okay. Sir, can you give any other example? I mean, other than the word prediction for recurrent neural network?
so basically any time forecasting options, right? For example, let's say weather forecasting if you want to do, right? So that is basically, so we're in question 4 here. So let's say weather forecasting if you want to do. So here the idea is that you want to predict what the next day's weather is, right? Let's say you have day 1 weather and so on up till day, let's say 10 weather, and I mean day 10 weather features whatever. Then what you will do is you'll take day 11 features, use whatever happened in the past to predict what will happen on the day 11, right? Will there be rain on day 11, or I mean will is a question, so how much rain or how much wind or how much temperature, all of these factors. So basically anything which has sequential ordering, that can be done using recurrent networks better because they are built in such a way that they can propagate information from previous states to the current state and all of that. That's again has been mentioned in the slides also, but that's the idea. Is that clear?
Yes, sir. Thank you, sir.
Sir, I think, yeah, here some memorizing is required basically. That's what I remember. In recurrent, wherever you want required to memorize the previous data somehow,
Right.
then you require a RNN. Okay.
Correct.
Now I have one more question on this. Suppose I have the live image processing. In general, image processing will use the convolutional network, CNN.
Right.
Now, if I have any cases where I have the live image processing, some decision I should take on the image, then I should
Right.
use the combination of CNN, RNN or only RNN.
So you generally try to use a combination of C and RNN. So there are multiple architectures which have come like this. So I'll give you one idea. So one possible way of doing it is like this, right? So let's say you have a CNN, right? And what you do is, let's say, okay, so for example, let's say video classification, right? Because in video you have both the things. You have images, and but you also have a temporal ordering coming into between these, let's say, frames that you have, right? So what you can do is you can keep on passing your frame 1 to, let's say, frame 10. Let's say a 10 frame video you have. So you'll pass it through CNN. CNN, whatever output it gives you, that you will pass through a RNN, right? So RNN, let's say the first cell, the second cell, and so on up till the 10th cell, whatever. And then whatever is the output, that is you will use to classify. Let's say between it's a video of a dog moving or a dog eating or whatever. I don't know, right? Playing and eating, something like this, right? So this could be one way, and this is the most crude way of doing things. There are multiple even specialized architectures which have come to do especially video classification, which work with CNN and RNN together. I mean the concepts of CNN and RNN together. Is that clear?
Yes, clear, sir. Thank you.
Yeah. And yeah, you're right. So basically, wherever we want to maintain some sort of a memory in the network, that's when we use this sort of RNN networks. Now, memory is a bit difficult to define, but the idea is that let's say there's some dependence on something that has happened before or something that exists before. Then we say that there's memory required, and we then try to use RNN. So again, so for example, another example could be, let's say you are trying to understand a paragraph, and randomly in the paragraph, for example, let's say there is something like some sentence and they say he went to something and then continues, right? So who does this he refer to, right? So this he refers to something that happened before, right? So therefore you need to remember something from here to be able to answer the question, who is this he, right? Who does this pronoun refer to? So that's called basically using memory, whatever you know till now. You use that to make a judgment about what this could be. So hence, in such cases, we use RNNs. All right. All right. Then question number 5. So for a fully connected deep network with one hidden layer, increasing the number of hidden units should have what effect on bias and variance? So any thoughts? What
Decrease bias.
decrease bias?
And once you decrease bias, for a very simple reason that it's fully one here. Just a minute. I'm not able to read the. We're increasing the number of hidden units. Increasing the number of hidden units means increasing the number of neurons in one layer.
Right.
Yeah. So see, even if you increase the number of layers or you increase the number of neurons in a layer, the chances are it is obviously going to decrease the bias. That means there is a tendency towards overfitting. Now, what will happen, which is a better one, more depth or more width is it is like it's a controversial question, probably maybe a research problem. Therefore, and once it decreases the bias and it tends towards overfitting, the chances of that it is going to have increased the variance on the test data. That is the logic I used.
Yes, correct. So increase the number of hidden units means basically you're adding more and more parameters to the network. So more parameters again is basically you will increase the variance. There's a high chance of overfitting, right? Because more number of parameters means you need more data to not overfit. So you will tend to capture more and more patterns in the data, which may not be the right patterns to capture. And but you will decrease the bias because of the fact that you are able to capture more complex patterns. Bias is high when you have a simple model. So increasing the number of units in the hidden layers generally will decrease your bias but increase your variance. Is that clear?
I think the question should add one more clause, given the data being constant for a given data. Because if I increase the number of data, obviously this answer will not be correct.
Right. So again, under reasonable assumptions. So I would say, so if nothing is mentioned about data, then that's so a fair comparison would be everything else to be same, right?
Everything else to be same.
Right. So because here I can also ask question. I can also ask them to qualify in things like, for example, let's say, is the loss same? Is the same way of the way you have taken the first initial weights of the neural network. So under the fairly reasonable assumption that everything else is same, then if I increase the number of hidden units, what will be the effect on bias and variance? That's assumption to be made. Yeah. Is that clear?
Yes.
Okay. Question 6 and 7. Yes. So you are given the task of predicting the price of a house, given the various features of a house, such as number of rooms, square feet, etc. How many neurons should you have at the output? So answer is 1, right? Because you just want the price of the house. It says 1 value. Okay, for a house, I want to predict the price, 1 number. Then what should be the loss function used to train the model? Any thoughts?
Mean squared error.
Mean square error, right? So again, I mean, as part of the course, also we have seen one sort of a loss function for training on continuous features, which is mean square error, and binary cross entropy, multi-class cross entropy. All of these are for classification sort of problems. Here we're not trying to classify, right? Okay, fine. Then question number 8. A convolution neural network is a deep network which extracts features from input given the operations performed on by CNN. So what is the correct sequence? Any thoughts? Why is B the right answer?
Because first you do convolution on an operation, a convolution operation. Then you reduce the dimension and therefore you do max pooling,
Mm.
then ultimately that's generally you will get some n by n matrix depending upon what is the convolution in the matrix. But
Mm.
you have to have a one-dimensional layer. So from there you have to flatten it into from a matrix into a vector.
Right.
And then of course you have to do forward propagation of the neural network. So that's how the answer is. That is 2, then 1, then 3, then 4.
Right. Right, perfect. Right. So convolution operation basically tries to find, is trying to look at, let's say, what features or what pattern should be there in that image at any layer. Max pooling sort of tells you, okay, I found this pattern in this whole, in this whole, let's say, image somewhere or the other, right? So it's like saying, yes, I found a pattern. No, I didn't found a pattern. It's not exactly that, but it's sort of a continuous version of that. And then and as Bhushan said, that at the end we want to classify, right, or we want to do something with this CNN. So we then have to because we want, let's say, one output or multiple output, whatever. At the end we have to need that. So because we have a matrix, we cannot work with the matrix directly. Rather we flatten it out and then forward propagate through a simple neural network, right? That's the idea. So hence the answer is 2, 1, 3, 4, which is option is B. All right. Okay, question number 9. So an autoencoder is a neural network which is used to create lower dimensional input representation. Which of the following is true about it? So first, again, we discussed this last time that it's a unsupervised algorithm similar to PCA. PCA also we're trying to get the number of dimensions to be reduced. In autoencoder also that's the aim, right? And in unsupervised, we don't have any labels, etc. Rather, we're just trying to reconstruct the same input. So that's each input itself is a target, which is exactly told in point number C, where the target output is the input itself, right? It can generate new data by learning the probability distribution. No, autoencoders cannot do that. There are things called as variational autoencoders which will do that, but not autoencoders. Then autoencoders can have linear encoder decoder. No, right? Because if that was the case, then we would just rely on PCA. But because of the fact that neural networks can handle, can do non-linearities, etc., that becomes a huge value add for this autoencoder problem. So we don't generally have linear encoder and decoder, right? So A and C are the answers.
See, what I've not understood is about autoencoders is its utility. Like convolution, you have understood the utility. RNN, you have understood the utility. Autoencoders का फायदा क्या है? अच्छा,
Right.
what?
So okay, so PCA का फायदा क्या है? चलो, let's talk about PCA, no? So we discussed about we said it is similar to PCA. So what is the use of PCA?
I think reduced dimensionality.
That's it. Autoencoder also same thought process. Now the question, so the question is, how do they reduce dimensionality? That's the question, right? So that is where the second layer, I mean the middle layer comes into picture. Again, middle is not right to say, but for now, let's just take this, right? So what we do, we pass some input X here. We're trying to make it to go through some low dimensional, constraining it to go through this layer. And then we're saying, I want the same X to be constructed back, right? And we're saying X hat should be similar to X, right? So now the point is, once you do this, you take, so this part of the network is called the encoder, right? And this part of the network is called the decoder. So then what you do is this encoder part of the network that you have, that acts as a feature reduction system. Yeah, feature reduction system, right? So basically, because of the fact that the layer here that you have will generally have less number of output units or whatever the number of neurons compared to the X input that you have, right? So what ends up happening, let's say if X belongs to some R power M space, the output from this, let's say I'll call this Z, right? Z will belong to some Rn space where n is less than m, and you try to keep it as less as much less than m, right? Then what you do, so then each x gets represented in the z space, which is in Rn space. Then you use whatever z's you get for a given x into your downstream task, which could be some classification or regression, whatever, right? By some other ML algorithms. That's the idea. Same thing you will do in PCA also. PCA also, the idea is once you reduce the dimensionality, right? The idea is we want to use it to, once you make less dimensions, you want to use it for some other task. For example, let's say classification or regression, whatever the downstream
Okay.
task is. Yeah.
Okay. Once again, some clarification, not about autoencoders. Many times we use the word dimensionality, features, parameters in a little confusing way. In a neural network, the number of neurons in the layer will represent the features, right? And the connection, the weights will represent the parameters. Is this correct?
Yes, correct. So let's say
The
you
number
have
of neurons do not represent parameters.
no, they represent features. You're correct.
Okay.
That's the way to think about it, and they affect the number of parameters, which is right, because obviously you have the weights being connected to all the neurons. So for example, let's say something like this, right? Let's say this is your network, and all connections are there here, right? Some classification task you're doing. So here these two are your number, let's say two neurons, right? And input dimensionality is 4, and these are the weights that you have. So all the weights and biases, they will become the parameters of the network, even these weights and biases. And the neurons basically, so how do they represent features, or how do they represent the lower dimensional space, is basically when you pass these x, your input through this network, and pass all of those weights through this network, whatever this output is there, that can be seen as some sort of a representation of the input again, right? But that is highly trained so that it can do this task well, whatever the task is. For example, let's say classification task, right? So it can be viewed as a feature reduction, but for the sake of this particular classification problem. That's the way of thinking about it. Is that clear?
Yeah, clear.
Now,
Sir, yeah, sir.
go
Yeah,
ahead. Go ahead.
can you go back to the previous slide, the autoencoder? Just now you done, na?
This one?
Yeah, exactly, sir. So what is my understanding? That's what I just want clarifying myself.
Go ahead.
See, as the sir asked the question, no, what is the purpose? So if I look into only the input layer and output layer, we'll get confused. But we know that this is mainly used to create the hidden layers. So in this case, once this layer is ready, we will discard the output and we will take the hidden layer, so that we'll this is mainly used for the create the hidden layers with a less dimension. That's the purpose of autoencoder. Am I right?
Correct. Yes.
Yeah. So the understanding here, if you see the output layer, it's the same dimension again. So that is no use. But the hidden layer, which is the center part here, that's a less dimension, but represent the original input. So this is the purpose of autoencoder, correct?
Yes, correct. Yes, yes.
Yeah.
Sir, one doubt, sir. Here we use encoder and decoder.
Hmm.
So what are the types of encoder and decoder? I mean, it is because in the D option we had linear encoder and decoder. So what is that term? If it is not linear, then what is it, sir? It is just we use encoder and decoder. That's all, is it?
No, no. So
There is
okay.
some algorithm behind encoding there, right, sir?
Okay. So in neural network, what is non-linear or linear?
Functions, ReLU function, ReLU and tanh, they're all
So,
non-linear.
Non-linear.
So where do they come basically? So once like this is there, let's say you have these inputs, and you have some let's say three nodes here again, right? And so then where does that non-linearity come in?
Active function after the linear, and we have active function.
Correct. So this at this node, what is happening is it will take the weighted sum of all the inputs and pass it through the activation function, some sigmoid or whatever.
It becomes non-linear. Yes, right.
It becomes non-linear. Correct. Now what I will do is I'll do the same operation, but I will keep on doing for multiple depth, like keep on going like this. Then at some point I will say, okay, now I will stop my number of dimensions, and I'll try it from this part onwards. I'll try to my input. So this becomes the encoder and this becomes the decoder. So, so encoder and decoder are themselves neural networks only, right? At the end, so you have input layers, hidden layers, etc. The generally the central most hidden layer is taken as the boundary of your encoder and the decoder.
Okay,
Is
Sir,
that
what
clear?
type of activation function is used, sir, for an autoencoders?
Uh,
Like when for feature extraction?
So you can use any and all activation functions. Again, the idea being that if you use only linear functions, they will not be able to capture non-linearities. But we want to capture non-linearities, right? So hence we can use ReLU, sigmoid, tanh, whatever you want, you can use. That's not a problem. And there is no one size fits all. It can depend upon from your. It goes from problem to problem. There's no one answer for this. Yeah.
Sir, what is that madam question previous one? No?
Hmm.
Suppose in that answer, the D, the last answer, if
Ah.
the linear word is not used, then it's the right answer. Am I right? That's what her question may be.
Yes,
Suppose we don't, yeah.
because autoencoders have encoder and decoder.
Okay.
That's how we say them as autoencoder. So it's an encoder part, it's a decoder part. It's not linear because see, if you want it, you can put linear also, but that's equal to doing just PCA. PCA is
Yeah.
even better because it does even more stuff on that linear mapping, right? So there's no point. So you will not use. I mean, you will not use a neural network which has a linear encoder decoder just to do the same sort of thing which PCA can do, right? So the idea here is they'll generally have a non-linear encoder decoder because you capture those patterns.
So in this fourth one, that's what madam doubt. In the fourth one, may either if you remove the linear word or non-linear word, then it both are answer correct. But linear word doing the wrong things there. Yeah.
Yes.
Yeah.
Sir, but autoencoders have only encoders, right, sir, for the neural networks? We don't use the decoder part of it.
So see, for training the autoencoder, you need the decoder part. No, because see, okay, so what is the thought process? Like, I think we discussed this last time, right? So where I said I have an image which has a dog, which has like a frisbee and everything. So the point is, what all information can you preserve in this Z, right? So what is required that you will know only when you are only through this decoder, right?
Okay,
That's
okay. To
so
train it, need it. But once to use it in the neural network, we will not need the decoder part.
We generally don't use the decoder part. I mean, there are use cases where people have tried to use it, but general use cases, you train the autoencoder first on whatever data you have, then you throw away this decoder. You use this encoder part to act as a feature dimensionality reduction system. You go from a high dimensional space to a low dimensional space.
Okay, understood.
Okay.
Yeah, that's because then actually we say PCA and autoencoder are similar. Any example that we can say that where PCA can be used, autoencoder cannot be used, or autoencoder can be used and PCA cannot be used for a similar case?
Yeah. So see, cannot be used is not first of all the question is wrong. In the sense, both can be used in all possible scenarios, not a problem, right? Wherever PCA can be used, you can use an autoencoder. Wherever an autoencoder can be used, you can use a PCA, not a problem. The problem lies in the fact that PCA cannot capture anything more than linear combinations. That is the problem, right? So PCA, if you remember, what it does is it tries to capture this maximum variance access or whatever. But at the end, what happens is it projects the data linearly onto those dimensions, right? So PCA can capture linear relationships very well, linear transformations in some sense, right? Autoencoders are not bound by this linear thing because of the fact that we can use nonlinear activation functions in these neural networks. So you can capture much more complex patterns. That's it. So, and see, then you can ask, okay, should I always use an autoencoder? No, there is no guarantee that autoencoder will always be better than PCA. No, we don't know that. We don't have any proof for that also. There's no theoretical proof. It depends on your problem statement. So whenever you generally get this sort of, you get into this issue of feature dimensionality, the first thing people try is PCA because it's very simple. It's a very simple, in a sense, computationally less demanding task to be done. People try PCA first. If it works, well. If it doesn't work, then they do the autoencoder and other complex approaches. Is that clear?
Yeah.
I had a question like, Autoencoders, one of the use cases training the inner neutron weights, right? Basically, in a neural network, because of that back propagation thing, the first layers of neutrons weights don't get trained properly. So to initialize the weights, they use the autoencoder, right? Is that correct? Use case of autoencoder.
Right. So,
And next, is it used for, like, just like PCA, is it used for any pre-processing, so that preprocessor to reduce the dimensionality, is autoencoder used for that also, or there is no such use case? Like PCA is typically a preprocessor where we basically reduce the dimensions, input feature set, so that we select the less number of feature set to which captures the maximum information. So we use it before a classification problem. Do we use autoencoder just like that to reduce the dimension, to reduce the, say,
yes,
runtime
that's
complexity?
correct. So
We
that's
use, okay,
Yeah, that's exactly what you mentioned, what I mentioned, right? So you use that to reduce the feature dimensionality. You go from a high dimensional space to a low dimensional space. Now, in the case of PCA, there is I wouldn't say there is a right algorithm, but there is some a heuristic to choose the number of dimensions, right? You say, okay, I will choose a number of dimensions where I can capture, let's say, 90% of variance or 95% of
hmm,
variance, etc. Here, there is no heuristic like that. Here,
okay,
the idea is you just keep on trying this this n, this value of n is you can fix, right? So you try keep on increasing this value of n until where will you stop? You'll stop whenever this error, the
okay,
reconstruction error, is
okay,
acceptable to you, right? So you say,
okay,
okay, is, let's say, point 0.1 or point 0.2, or based on whatever units you use, right? So you will say, okay, so point 0.2 I'm fine, so there you will stop increasing this.
okay.
That
I
becomes your
Okay, I
trained.
got it. So these are two separate use case, right? One is neural network inner layers ka
Yes.
weightage training, and another is the dimensionality reduction. That is, it has two separate use cases, right? Then that means autoencoders.
Yes, yes, yes. Huh.
Okay.
So, see, again, see, training inner layer of the neural networks. I
Uh,
haven't seen that much, but
okay, the
I'll tell.
ma'am said in video actually that one, that
Yeah,
use case.
I know. So I'll tell you in what sense I've heard it. Okay.
Hmm.
So, okay. So let's say you have okay, we'll spend 5 minutes on this issue. It's an interesting issue. So let's say you have an image, okay, and there is some circle and whatever, right? Now you've trained a network to say whether the image has a circle or not. Very simple sort of a use case, right? No, but the problem is, for example, let's say you can have a lot of background noise here, and the circle can be of different colors. It can be of different size. It can be, for example, here, and all of that. There are different issues, and you get a good amount of data set. You train a network like this, right? Now, what people have found is that for the same image, let's say, for the same image, the model was saying correct. Model was saying yes, there's a circle here. Now, by changing some pixel here, which doesn't matter to this circle, circle is same. Only one pixel got changed, but the model started saying no, right? So what ended up, so then people thought, what ended up happening here? Why did model fail for something that is so trivially different? What it seems like, neural networks seem to capture patterns which are completely, unknown. Some random feature it has, learned, some random pattern is learned, and because of this particular pixel changing, that broke the way the patterns that this network has learned, and the model started saying the answer is no, right? So now, then what people said is these neural networks seem to be learning some very specific patterns to your training data, and may not generalize very well to the test data. So one way of counterbalancing that could be adding this autoencoder sort of thought process. So how does it come? So let's say you have a neural network, right? Some neural network here, and then you're trying to output some, there's some output layer, output node here, right? Now what you will do, you will say, okay, from this particular second layer, you should also try to reconstruct the input. So this is X, output should be Y, but you should also try to construct X hat. So now what is happening is these weights or these layers have to capture the concept of this X, right? I don't want to use concept. Let's say some features of X which are which say that okay, X is some good image or X is some valid image in some sense, and also while this at the same time also do the classification correctly. So in such cases, what you generally have is the loss is basically your cross entropy loss, let's say a binary cross entropy loss plus the autoencoding loss. You say X hat minus X should be, whatever. So you try to minimize this objective. So in that cases, it helps. So here, if you see these weights that you have to do two things. They have to also support the network to do classification well. They have to also support this part of the network to do reconstruction well. So in this way, you are learning the features of the the image more strongly, and not just trying to do say, this classification task. In that sense, you can say that autoencoders are also useful in initializing neural network weights, having a better initialization. More than better, I would say robust initialization in some sense. Is that clear?
Yeah, I get it. Basically, it does two things at a time, basically. So one is the X hat construction, and another is the final output, that is a classification thing which is captured out there. Am I correct? Like, yeah.
Right, right. Yes, yes, correct. Y also has to be accurate. Okay. Yeah. So
Sir,
SK, you're
autoencoders, they used without the neural networks, sir? Like PCA. PCA is used in the non-neural networks also, right?
No, no, no. So no, no, no. So autoencoders are the fact that you can use neural networks for this sort of reconstruction. So autoencoders means that you have two neural networks. Something that takes you from high dimensional to low dimensional and then low dimensional to high dimensional. Again, generally speaking, there are many variations out there, but generally this is the idea that both are neural networks, and that's how autoencoders became a bit, famous in the sense that because we can use neural networks which can capture very complex patterns also to do this sort of a transformation.
Sir, this autoencoder can be applied in any layer, right? Not necessarily in the first layer. In any of the layers, it can
Any
be
layer, yes, any layer you can do that, but you should be very careful. See, because uh, for this use case, for example, right? So let's say if you ask that the last but one layer also has to do this XHAT construction, right? So then what are you saying? You're trying to make sure that the complete information about X is there until the last layer, right? Because it has to construct X hat from here only, right? So therefore, this is some sort of like a hyperparameter you can choose, because you have to decide at which layer will you ask the network to deconstruct the input. So I would say again, it's an empirical way of solving things only, but you get the idea, right? So if you do at very last layers, you are forcing all the information of X to be present until that last layer. So the amount of network that can be used purely for classification is very less in this sense.
in the last layer, yes.
Yeah. So I would say, I mean, this is something that I guess has to be done empirically only. But yeah, this is the idea.
Sir, I have one basic doubt, sir. I mean, the word heuristic,
Huh.
what it says, sir? It is learning itself is called as heuristic, right, sir? I mean, in this machine learning concept, that word, what it actually means, sir?
So heuristic is, I mean, at least the way I understand this, it's some a rule to guide your, let's say, process or learning, right? Guide your learning. That's it. That's all I understand with heuristic. And when you say rule, so then the question becomes, how do you implement that rule for the particular learning process, right? For example, now let's say when you say heuristic for neural networks, it has to be in some sense of something which is differentiable, because at the end neural networks will try to differentiate the loss and try to move in that opposite direction of gradient and all of that, right? So but then, for example, let's say if you have some sort of a genetic algorithm is one other approach of solving problems. So there the rule can be very different way it can be specified. So it's just a rule to guide your learning process. So you say, okay, move towards. So let's say in case of neural networks, we could say that moving towards the least, moving towards the gradient, opposite gradient can be taken as a heuristic because it's likely that you will find a minima there, right? But it's possible that you might go to a saddle point, then you have to solve further, solve in different approaches and all of that issues. So a rule, it's not that it will work always, but it's just that some sort of a guidance. That's it.
Thank you, sir. I had this major doubt actually. Understood.
Can I say something?
Who is this?
SK.
Yeah, go ahead, SK. Yeah.
Right. About heuristic, the context, the sense, the meaning, the connotation with which I've seen it so far in this course is no different than how it's used actually in all other places. And if I had to answer the question that you were asked, I would say that it's a rule of thumb, a convention, a tradition, or something which has been seen to work so far, but which has no reason, no justification that we know why it works. And that's pretty much what it is. It's basically empirical standard practice, and you implement it. That's how I would understand or define or answer that question.
Right. So we don't have theoretical grounding for that rule or for that rule, but it seems to work in practice. All right.
And about my question.
Yeah, go ahead.
Right. I mean, what I posted on the forum, and I was just waiting for an answer because I mean,
yeah. So yeah, I saw your question, but see, see, variational autoencoder is nowhere in the course. It has been even mentioned, if I'm not wrong. So assuming that this was meant to target something like a variational autoencoder, that is not. So first of all, that is not. It's not right for other learners also in the first place, because of, the way the course has been mentioned. In that sort of a setting, what is neural network supposed to do? And in sorry, autoencoder is supposed to do. In that, it cannot generate new data from the property distribution.
I agree with that much, but the statement itself is not false. So, I mean, shouldn't I also get the equivalent marks for A and C?
Again, so last time we had this same sort of question, right? So where we
about
had
C, about the C tending to infinity thing.
No, not that. Not that. There was a question about, okay, yeah, so the RBF kernel, which is the most commonly used, this one. So I understand, in the course, videos and the material and all, there was no mention about what is commonly used, right? So that would require you to go beyond what is there in the course. So I've asked, we're on the cusp about finalizing something about that. So then in the same thought process, right? So then in question 9, then that doesn't apply then, right? So I mean, we cannot go back and forth here.
No, I didn't get that. Someone was clearing their throat, so I didn't hear what he said.
So last time we came to a conclusion that okay, it is not fair to have some question which is not mentioned, or there is no mention of something related to that in the course. For example, let's say I am talking with respect to the question of commonly used kernels for SVMs. Now, the same thing can be mentioned here, right? So I mean, in one case,
yes, you can. So the concern there would be to not penalize the people for that 1/3 mark they would lose because they did not mark option B as correct. But then the person, I mean, I happen to know that. In fact, actually, I went and looked for it, and therefore I was able to quote the sources that I did in my post. So how would, I mean, equivalently, how would it be fair to me, to know more than what was expected, or to have made more effort than others did? All I'm saying is that at least I should also get the marks for A and C. And also the thing is, I mean, I mean, restricted to the scope of the course, okay. But then the phrasing of the question then also becomes an issue, because it's like it's equivalent to saying that a variational autoencoder is not an autoencoder, isn't it? I mean, only if the solution itself basically says that it talks about, when it shifts, it makes a distinction between conventional autoencoder and something else. If you look at Bishop and if you look at Mitchell, They do not mention variational autoencoders. They mention lots of other types. Sparse encoder is the one that comes to mind. So every time we see an adjective before an encoder, are we now before an autoencoder, then are we supposed to now start presuming that it is not an autoencoder? Is I mean, essentially, how do I interpret the question becomes, what sows doubt in my mind.
So I would say, whatever is the course content that has been covered, that should be your end all and be all. I mean, that's something that I understand worth fighting for. This one I really can't agree also. So I mean, see, you put on the post. So I would say let the course TS take a call on this. Again, see, because I don't have control over what the marking scheme is, who sets the questions, nothing, right?
Oh.
I'm just here to help you understand what the concept is and is it right or not. So I understand that variational autoencoders are a type of autoencoders. They learn new data, they can generate new data by learning the probability distribution. All that is correct. In the scope of this course, variational autoencoders were not covered. So this is not expected out of anyone for that matter. So
but not expected, but still, I mean, those are two different cases, isn't it? I mean, to mark it wrong for that reason. To say that you're indifferent, to drop the option B is one thing because you're not expected to know. But to put a statement which is true and then say that because you said it is true, it is wrong.
Yes, SK, I read your whole post. I agree with you. My point is very clear that since you've already pulled on the
Okay,
forum,
so not your jurisdiction. It's not your remit.
Because it's not in my hands. That's the whole point.
Fine, fine. Okay.
I
just need to know.
The marking scheme are not in my hands. That's the
fine.
Sure. Okay. And any other questions on autoencoders, usage, training, etc., etc.? Anything on that?
PCA itself is a single layer linear autoencoder, right?
Yes, but it also has other constraints also on the fact that the dimensions have to be independent. I mean, orthogonal and all of that. But yes, a linear autoencoder with some constraints. Yes. Yeah. Okay. Question number 10. So in a simple model with 8 neurons in the input layer and 5 neurons in the hidden layer and 1 neuron in the output layer, what is the size of weight matrices between hidden to output layer and input to hidden layer, right? So again, this should be straightforward. So we're asking hidden to output, that's 5 to 1 because you have 5 neurons here and 1 neuron in the output layer. So you need a 5 cross 1 matrix to go from here, from this hidden to the output layer. And then you have a from input to hidden is 8 neurons to 5 neurons. So it's be 8 cross 5, right? Is that clear? So the answer would be A.
Yes, sir.
Okay. Yeah. Okay. Then question number 11. So if you increase the number of hidden layers in the multi-layer perceptron, the classification error of test data always decreases. True or false? Any thoughts? We just discussed this a while, but why is it false?
Because it does not always decrease. It flattens after some time.
Overfitting also.
Overfitting and all of those
Works
issues.
on the training data, on the test data, it will not.
Right. Right, correct. Because the idea being that it can capture more complex patterns, but are those patterns the right patterns to capture so that the test data would be correctly classified? We don't know. So hence, it's possible that it may not always decrease. It can also increase.
Sir, clarification on that. If same question, if it's the instead of test data, train data, then it will always decrease. That's a more clarity, am I right? That madam told same thing only, correct?
Yes. So yeah, so training data, it will always
no, yeah, that's why all ambiguity is there. Just
not even, it won't be even always. It will be asymptotically decreasing.
It will never decrease.
It'll be constant of that, or I don't know. That's what there's some small.
So I would say generally it would decrease the data. So train data error will generally decrease only as you increase the number of hidden layers or whatever in multi-layer perceptron.
It will not increase. No? Say the answer is if it's not increased, then obviously we'll accept this answer. I'm telling you train. I'm not asking test data at all. I don't want to confuse anybody. It's a train data I'm talking about now. So train data, when you increase the layers or whatever units you increase, in general tends to decrease. Of course, it may be constant after that, but it will never increase.
It's very rare unless
yes. As
Yeah.
well, I'm not in parameter. The data I'm just in correct, no?
Yeah, yeah. Yeah, so training error generally will decrease. That's all I can yeah.
Yeah.
That's
Not necessarily, sir. Hello.
go ahead, yeah. Go
Not
ahead.
necessarily. Actually, we in a code I got there, we increase the layer, but the accuracy has dropped very drastically.
Drastically.
So not necessarily.
Not necessarily, right? So I would say generally it will decrease. That's it. So there can be cases where things can go haywire. Yeah. So again, see, neural networks we still don't understand, but error on the trained data will generally decrease. That I can say. Generally, in the sense, in most of use cases, that's what happens.
Clear, sir. Clear. Yeah.
And then in test data, you are saying that it may not always decrease. It can increase.
Yeah, it can increase, decrease, anything. Yeah, that's true.
Okay. Because after a certain point, I think it increases. That's the point where you have to stop learning.
Correct. So we treat that point as overfitting point, and we say that okay,
As an
after
overfitting point.
yeah, there's no point going forward. Yeah. Yeah.
Sir, I have just a doubt in terminology, like validation set we keep, and because test data we never able to access, right? Test data is a real world we don't. So
Yes.
here, how we measure the test error, like validation test set as we take as a testing or what?
So in
But
this
it is a
question, what they're saying is error on the test data. So we're not about validation data. So let's say there was some test inputs that came. You trained the multi-layer perceptron using validation, cross fold, whatever, etc. You did all those things, right? At the end of the day, you have a trained model. Let's say you have let's say some test data has been generated now, and it has been passed to this network. Now, what can you say about the error on the test data? That's it. This question talks about that way. That's how I would interpret it.
in general, I wanted to know that validation set is a part of training set itself, training data. But test data is completely different. Well, we should not mix in training, right?
Yes, true. Yes, that's correct. Yes, and validation data also so once you separate the training data into
Two
sub
part,
actual
some part.
and let's say validation,
Clarify, sir.
validation also is not supposed to touch the trained data. That's how you should treat it, because validation data generally is used to set your hyperparameters and all of those sort of things, right? So hence, so whatever metrics or whatever information you want from the data, only training data you will use to train your model and do whatever extra stuff you want. You will use validation as a estimate of the the test error, right? And using that, you will set your hyperparameters. Once you set the hyperparameters, then you're done. Then you will use it on the test data and just get the test error. That's it. You cannot do anything on the test error.
Okay, thank you.
Sir, can I clarify
Can I?
just more on that?
Go ahead.
Sir was telling that actually, we never get that as real world data. But in reality, when we develop a model, whatever data we have, we will group it as a test data and train data. The test data usually will keep some 30% or 20%, whatever. Now, in the train data, we'll again subgroup it. One is learning data, one is validation data.
Yes.
The learning data will use for the learn the model. Then we do the validation to hyperparameter settings. And finally, we fix the model. We've done it. Now we should tell the world how much error I have, how much my accuracy. For that, I use the test data and declare my accuracy, precision, and all things, so that the people can use it.
Perfect.
This is clear, sir. I think this.
Yes. Perfect, Satish. Yeah, that's how we do a machine learning model training.
Yeah.
That's
Yeah.
okay. All right. So then,
can you, sir?
Go ahead.
Can you hear me? Can you clarify that error of test data?
So error on test data is whatever test examples you have, you will pass it through the network, right? So test data, let's say, or let me call it X test, right? And Y test, corresponding Y's, right? So you will pass your X test through your network, right? You'll get F of X test. So this is basically your Y hat test, right? So what is the prediction that you're making on the test data? And then you compare that with y-test, actual labels or whatever, right? In case of, if it's regression, you will calculate the mean square error. If it's, for example, let's say the classification problem, you will do a binary cross entropy, all of those things. That's the test error. That's it.
Based on the test data in the neural network, we are going for the back propagation.
No.
Based on the error occur in the outcome.
Error occur in the output layer, but on the train data, not on the test data. Okay. In the same way, you have a X train and Y train, right?
Yes.
Then what you will do, you will do this same thing. X train, you will pass it through the network. Let's say F is your network. You will get Y hat train. Compare this with Y train, true labels, right? Or true labels, or whatever you want to call it, right? True data, true outputs. Then you will, whatever error is it, that you will use to back propagate and train your network. You will do this after training, after setting hyperparameters, everything. Test data you'll pass it once through the network, get the predictions, compare with the actual values, and report your test error. This is exactly what you will report to the world, as he mentioned just now.
Sir, generally, to summarize my understanding of validation versus test data. Okay, training data we know that is for learning, and
Right.
test data is purely for assessing the accuracy of the model. Correct.
Correct.
And validation is something which we use for tuning the learning hyperparameters.
Yes, that's it. Yeah, that's true.
Okay. So that is the reason that in the test data, we don't bother about back, because back propagation is a part of learning. So in test is we only give the input, we measure the output and see that whether the output is matching and calculate the accuracy.
Correct.
So,
yeah.
Thank you.
Yeah. We also don't back propagate on the validation data also, by the way, right? See, back propagation happens only on the training data. Validation data is used to set the parameters. So you say, okay, I'll try different parameters. Hyperparameters,
so,
try different values, see what is a validation error. Then you choose one of the combinations of this parameters, and then that is set as a final model, which is then tested on the test data.
Yeah, hyperparameters for a neural network is the number of layers and the depth of each layer.
Yes.
Only two, right? Anything else?
So the activation function, the way you initialize your the first first time that you choose your weights, all of those are hyperparameters.
Initialization weights and activation function, but activation function always we choose the ReLU, right?
No, not always. No, there's no rule for that. There's no rule like that. There are many activation functions which have come after ReLU and even were existing before ReLU, but ReLU got famous because of it being successful in the image CNN tasks in CNN networks.
Okay. So yes, okay.
So yeah, number of layers, number of nodes in each layer, then your activation function, then your initialization, approach, whatever you use, all of these will become part of your hyperparameters. And then let's say just now okay, let's not complicate, but yeah, these things. And then, for example, let's say if you're trying to do some L2 regularization or whatever, right? We also have that parameter for regularization, like lambda mod. We would do this, right? Lambda norm W. So that lambdas. So all of these stuff, all of those come under your hyperparameters, right? Based upon some optimization algorithm that you use. For example, let's say there's something called as an Adam optimizer. So Adam optimizer has things like what is your it is something called momentum updates and all of that. So that has some parameters in it. All of these are hyperparameters, something which cannot be learned from the data, right?
Okay.
That's all being.
Yeah. So the only thing that can be learned from data during training are the weights.
Yes. Weights
are the only things we learn.
Yes. These are the
outcome of the learning process is arriving at the right optimum weights, right?
Correct.
Okay.
Yeah.
Okay.
So all these are hyperparameters. So parameters is what in neural network? These weights and biases.
Yes, that's it. These are the
Yeah,
parameters.
these are the parameters, and the left hand side is the hyperparameter. Okay.
Even the base is a hyperparameter because bias is a hyperparameter because you don't
No, no, no.
you
No.
don't learn the bias, right? Do you learn the bias?
Bias also, no?
Oh yes, W1, B1. No, but
B1.
B1 is a constant, but W1 is what you learn, not B1.
Yeah, we had this discussion before in the last class also that yes, so bias generally what people do is you set the input to be always +1, and whatever is the weight associated with it is called a bias, because the way
Okay.
it affects the output is basically just adding something, which is
Okay.
how bias is termed, is
Yeah.
defined in this
Yeah,
particular
generally, sir, generally in some books to avoid confusion, bias also is considered as W0.
Exactly. Yes. So it's taken as W0, and X0 is set to be +1 always. That's how we.
Yes.
Hyperparameters are not counted as a parameter of learning any model. Like most of the CNN, whenever they ask number of parameter, they only say about the weights.
Yes,
But,
yes, yes.
they
Yes,
don't
yes.
talk about like ReLU or max pool or some averaging. They
No,
left tail.
no.
Yes. Okay.
Yeah. No. So whenever somebody says, okay, there are billion parameters, it just means weights and biases. So these are all different from parameters. So these are all different things that are generally not counted also in terms of number of parameters, because parameters is basically tells you how much like what all can be learned from the data, right? So when I say billion parameters, I have to learn so much from the data. That's how people try to when they talk about parameters. Hyperparameters you have to do using either validation set or whatever, and or either some heuristics, which basically, as we clarified right before, that something which has worked for people in the past, you either use that or try different values here.
Sir, as a general knowledge question, this chart GPT, they say that billion parameters, that means, is it billion or million? I just want to know the quantum of the size of learning parameters.
I think it is billion parameters. Million seem we crossed million long time back actually. So I
Okay,
think it's,
billion parameters, that means billion weights it
yes,
learns.
yeah,
Okay.
billion weights and biases, yeah.
Okay.
Okay, next question.
Next question. What is the range of output values of a sigmoid function? 0 to 1. That we know very clearly. Single perceptron can compute XOR function? No. This is mentioned in the notes also. What are the steps for using gradient descent algorithm? Answer is said to be A. Any doubts on why A is the right answer?
No doubts.
No, sir.
Right? So first you initialize, then you pass through the network, get the outputs, you find the error, and you go to each neuron to change its respective weightage on the error, and then you repeat until you get the best best weights for that network. Last thing, a backpropagation algorithm applied to two-layer neural network finds a locally optimal solution which may be globally optimal, right? We cannot say anything about the global optimality of in especially in terms of neural networks, because there are no mathematical tools yet which guarantee these things, and so always is not right, never is also not right, but because it depends on the problem at hand, and finds a locally optimal which is never globally, again that's also not true. It'll find a locally optimal and which may or may not be the globally optimal solution. All right, that's question B. Option B. Any other doubts?
Can you brief about back propagation process? Back
uh,
propagation.
Right. So, but okay. So, what brief in a sense, like what do you want to know? What is unclear in that?
I want to. I'm not clear about that process. As we started discussing that when we get an outcome in the error in the neural network, it goes to the back propagation to reduce the error.
Ah.
Am I right, sir?
So okay. So I'll do one thing. I'll mention it in like 2-3 minutes. But for a deep, I would say, just go through the lectures. If you still have questions, I would
Just to
suggest.
give a glance about it, I go through the man's lecture, but I
Right.
have a slight doubt on it. As per the lecture, I understood when we get an error in the outcome, we go for
Right.
a back propagation to reduce the error in
Right.
the first hidden layer. In that layer, if we get an error, again we go for the back propagation for the previous hidden layer. This is
Right.
what. So what we do actually in the back propagation? What is that? Is it a function or a process? I want to know that. That is the thing I want to clarify.
So see, back propagation is basically, so let's say you have a neural network. Let's say I'll take a 2-layer neural network, right? Something like this, right? Now, when you get an error here, so because see, whatever output you got, some output you got, right? Some f of x, whatever x you pass through this network, f of x is what you got the output, and you compare with, let's say, with the true value, that is y. So we define the error in some way. So error is basically some f of x minus y squared. Let's say we're talking about regression, right? Now, because this f, the output that you got, depends upon the weights on biases of this network, right? So let's say I will, in general, call them as w, all the weights and biases, whatever, right? So let's say I have w here. Now, the idea is I want to update each of these w. Let's say w new is w old plus some eta, not plus, minus eta dou e by dou w. So the idea being, what is the derivative of the error with respect to the weight w? Uh, then you subtract that from w. Now this is why, because this is the idea of gradient descent, right? Now this is all okay. The issue what comes is when you say, for example, let's say the middle layer, or let's say this layer, for example, when you want to update the weights of this layer, you don't, there is no error function which is coming, which is present here for these weights, the weights in this layer. You have a error signal coming in, right, which is exactly this. Here we don't know what the true value should be. Rather than, what we do is we represent this fw. We try to look at its effect of this particular weight on this fw throughout all the other nodes, right? Because see, this weight, whatever is there, affects this the output of this node, this node, this node, all these nodes, right? And therefore affects this output in a much more complex way. So what you do is you try to take the effect of this error on this node through all of these networks, right? So that is the thought process. So because we don't have the true value that should come out of here, this is called the back propagation. You're back propagating the error to that node from this last layer or whatever, right? This is
Sir,
what.
sir, as I understand it now.
One second, Gopal, one second. So the idea here is the approach is the same. Dou E by dou W only you will do. There is nothing special about it. The point is you can look at it as you are back propagating the error from this particular node to this area. We are saying how much does this node contribute in the error that has been seen until now. That's the idea. Okay. Yeah, go ahead, Gopal Krishna.
Yeah. So as
So
I
we have to
understand,
change the weight.
We have to change the weight. Yes.
Okay.
So we want to keep changing the weight so that we keep on going towards the local minima where dou E by dou
So
W
to
becomes.
reduce the error, we are raising the weight. We are changing the weight. Once
Yes.
we does not get the error at that stage, the weight updations will not happen.
Yes. So that's a bit difficult to quantify. It's possible that you will not you will have error, but you will not be able to reduce it further, right? Because of this derivative. If you see, it's dou E by dou W. Just because the error became zero, just because the derivative becomes zero, doesn't mean the error is zero. I hope you understand that.
Yes.
Right? Yeah.
sir, just to understand the word back propagation is a special significance for neural networks, just because neural networks have multiple layers. For
Yes.
example, there is an input X and the output is Fx. After going through so many layers, it is giving an output Fx. So the really error measurement happens in the output layer. Actually, the last layer we keep measuring the model output and the actual value, and we come to know that error. So we don't know that error at the output layer is caused by what kind of weights responsible. To understand that, we are flowing it backwards towards input. Input, correct? So
yes, that's correct.
Yeah. So, for example, hypothetically, let us say that the old regression, right, linear regression, a non-neural network. In non-neural network, if you can have a parallel to the neural network, the linear regression and versus neural network, but the same kind of problem, there is only one layer. There is only one layer. Okay, one layer. So there is no question of back propagation. Actually, in the linear regression also, we are computing the error, but there is no propagation because that is immediately the previous error is the input layer itself. So there is no concept of propagation there, because only if there is more than one layer, the concept of propagation comes into picture.
Yes, yes.
Correct? My intuition is it?
And as I said, like there's nothing special about it. You're just trying to do dou E by dou W. That's it for every step. It can be viewed as a process where you're trying to back propagate the errors. That is, take the errors and moving towards the input layer, and you're trying to look at how much did this particular weight affect the output, have an effect on the error in what way. And it's complex, and therefore we do this sort of thing. You look at all possible effect that you have on the next layer, and then you get the error at this layer, and then you update your weight. That's it. Okay. All right.
I had
Sir,
a
when
doubt.
we implement,
Hello.
Go ahead.
Hello.
Yeah,
Okay,
so
when we implement, okay, 2%. Okay, go ahead.
so I had a doubt in the current lecture series. There is eta, and another is some another function. What did it call? Eta and yeah, that one.
Delta
Eta and delta.
And yeah,
Epsilon.
This epsilon, this delta.
yeah. So I wanted to know the difference between the two. What is
Sure.
means is that epsilon equal to, like, say if you are aiming accuracy of 90%, then eta is 0.9 or 1.1, I don't know, whatever be it. Is it that is my understanding correct?
Okay, we'll come to that. Jitendra, did you have a question on this or the previous thing?
No, a previous one. When we implement that, the back propagation is just only once for a given one sample, when we forward and backward. So that eta is there, like learning rate. So how we can ensure that the parameters are like reduced, or in next sample it keep iterating? Means there is only one loop, right? There's no again forward and backward. We do only once, right? Feed forward and then back forward. Then we update the layers.
Right. So okay. Ideally, so generally speaking, we have two loops in this sense. One is called epoch loop. Let's say 1 to 100 or whatever, and then you have these sample loop. You're saying n equal to 1 to capital N, let's say, right? If you have capital N 10 examples, then what you do is you pass this xn, for example, through the network. You look at what is the prediction, error, whatever, you update. All of that happens here, right? So in this inner loop, you have forward propagation of xn, get the prediction, update all the ways to back propagation. That is once in this n loop. Now you will do this capital N number of times. Then you will repeat this whole process even more, like let's say 100 times or whatever, right? And here you have multiple choices. You can do either complete all x together, right? I will not do one sample by sample, right? This is called as, I guess, batch gradient descent. If you do single ones, then you'll have something called as stochastic gradient descent. Then you have mini batch, where you choose a small set of this one, and then it's called as mini batch, all of that. But the point is, you do this. So in this inner loop, Once you will forward propagate, once you will back propagate, all of that is done, then you'll have an outer loop which does this multiple times. It's like telling a child to learn to write A, right? On let's say some board, right? So you will not say, okay, you do once and you're done. Like it'll be expert. No, you'll make
Epoch
it right.
is not for a particular one sample. It is for whole one training.
Whole data set. Yes. Whole data set. So you're asking how many times should the network see the whole data set? That is what epoch generally represents.
No, that is one epoch, or that is a n number of epoch. If suppose n number of times we are running that whole process.
Yes. So n number of times for each epoch, you will go through the whole data set.
Whole
so
data set.
Number of times you will go through. In this case, I'm giving 100, but yeah, n some e whatever.
And we will keep the weights of previous epoch final means for the second epoch, we will use the optimized weight of the first epoch. What was the first epoch? As in when the epoch loop runs second time,
right?
Say first time the epoch loop ran and the inner loop where say we used per sample basis, we did not batch basis, and we got the and we went forward propagated and then back propagated for each sample and got the weights. First epoch finishes and we have got the entire param set, that is the weight set, weights and bias set. For second epoch, when we start, do we start from that point of weights?
Yes, we start from that point of weights. In fact, see, that's exactly what I was saying. Here in this inner loop, you're going forward propagating and back propagating. So what does back propagating mean? You're updating the weight itself. So let's say epoch equal to 1, n equal to 1. You did this process, right? Back propagated, whatever, right? Now, same epoch equal to 1, n equal to 2. Whatever the result was there, that is what you will use here. You will update on these weights.
Yeah, so here small n is the samples, right?
Yeah,
small n is sample. So why are you telling n equal to 2 out here? So I am thinking after each sample is updated, all the weights are changed, right? Like not only correct.
First, yeah, I meant first sample. N equal to first sample I use.
And n is equal to basically epo. Correct. And I now want it like epo equal to 2. Epo equal to 2 is equal to n is equal to capital N will be the starting point of the first epo.
Yes. So whatever got updated here, that will be the starting point here. So for epoch number 1, n is equal to nth in whatever sample that we had. You did the forward propagation, back propagation, weights are updated. Now, when you start the second epoch, and again for the first sample, you will use whatever was updated here as your starting point. So your W old becomes the W new in this iteration. That becomes the W old now. You'll start from there. Yeah, go ahead. Who was the next one?
Sir, so in each, while running epochs, multiple epochs, the assumption we are making is the weights ultimately converge to some optimal value, correct? Convergence.
Yes.
Convergence. Okay. Hypothetically, this convergence is possible only if there is a pattern in the data. For example, if the data itself is a random, so the convergence cannot happen, right?
No, again, see, Gopal Krishna, here's where the point about training, testing, validation comes into point. So let's say if you have a very complex model, what it will do, it will learn those random patterns also, just because you had a random sample. Because see, the point is your training data is a finite sample. Because it's a finite sample, I can always look for some or the other random pattern in that to get my output, right? So your training error will reduce as long as you keep on increasing your network, right? It'll learn some or the other pattern. The holy grail of that system would be checking on the test error. And you will
That means it can learn any function, even some random also it learns. Okay, there is nothing like non-converging at all. Only thing is it may take more epochs for coming out with.
Yes, depending on model complexity, etc., it can take more epochs to converge. Now, this issue is actually because of the fact that we have a finite training sample. Because in a finite training sample, when you say a finite training sample, you have a finite random sample. So in that there is some or the other pattern, right? I can always do some or the other thing and try to classify it, right? Or get some regression output, right? So in case you had infinite training data, then your model will never converge, because there is no true pattern in it. So your training error will always be, it will always try to say, oh, something went wrong. Now I have to change it. Something went wrong, and so on. It'll keep on doing that.
Sir, in
Yeah.
case of
Just one
infinite,
more
sir,
question. In autoencoder, suppose dimension is reducing, then back propagation we are going how go lower to high dimension.
Yes.
Like that will also affect the, like how we do that. Suppose one I am familiar with whatever is back gradient we get back in the CNN model. We put some where max full we did there we put something and rest we put as a 0.
Okay.
So what are the other, like in case of autoencoder, how we handle like going back?
No. See, again, see. Okay. So in autoencoder also, where we, yeah. So here, right. So this is what the thing is, right? So let's say let's say we have MSE error. Okay. So what you will do, you will have f of or fw of x minus x. That's it, right? This will be your error, actually speaking.
Baba?
Who is that? Yeah, okay. So you have fw of x minus x. Now this w is all the weights of these layers, and all of these complex weights that you had. All of those weights are part of this. So all of them you'll try to update. Now let's say one question which I think you're coming towards, let's say if you use something like a max pool layer here, what will you do in this layer? Like there is no inverse available there. Right?
Yes, that's I mean need to yeah, we reduce, then how we go back in case of autoencoder or something. There we use decoder or what? That's my question.
So there are some hacks on how to how to get that inverse max pool. There is some hack available, but I mean there is no surely there is no a right answer to it, because max, if you do, it will just break down all the other information is lost. So hence people try to use something like average pool or something like that. That's what people try to do. And we also have
small just okay, go ahead, sir.
So we also have something called as I think inverse convolution or something, upscale convolution, something like that. So convolution brings down the dimensions, right? There's the inverse operation which takes a smaller image and makes it to a larger image. So those things are then generally applied. In case you want to use a convolution neural network for an autoencoder, then these things are
upsampling kind of stuff.
Upsampling sort of, yes, upsampling sort of things are done. Yeah.
Okay, you mentioned a sequential order data. What do you mean by sequential order data?
So as I said, right, for example, let's say in weather prediction system, right, weather forecasting. So let's say you say my current weather depends upon what my past 10 days weather or past 20 days weather is, right? So that's a sequential data, right? For that's one. Let's say text is a very strong example of sequential data. Speech is again a sequential data, right? All of the videos are sequential, right? Okay. Anything else?
Sir, a small doubt on the epoch. Can you come down, sir? The
Epoch?
for loop. Yeah.
Where were we? Yeah, here. Go ahead.
Yes. That's why.
I'm sorry. What question you had?
Yeah, I am just looking for some clarification on my understanding here. See, epoch is that how many iteration we are doing. Okay.
Right.
Now, when I do the iteration, we have the data. Like let us see the 1,000 data I have, 1,000 samples I have. So in general, what we'll do, we'll break like for example batches. So we have the batch of 30 samples. Okay. So we will give the inner for loop 130 number batch. We'll do all propagation and all backward propagation. We'll do it, and we have now one weightage. Weights are there. Okay.
Correct.
Now we will repeat same thing for the next iteration again. Next 30 samples. Am I right?
Yes.
Because if, every time, so that means if I have 1,000 samples, if I'm doing a 30 samples, every epoch will be one new samples. So that finally my weight will be coming to the normalized or whatever value. Am I right? Not the same samples showing to the again no meaning. Am I right?
No, same sample is used.
Same samples. This N is basically all the training data that you have.
Yeah, my question now. Suppose if I take the first 30 samples, okay?
Yeah.
And I given in the for loop the 34 that I equal to 1 to 1 the first 30 samples. Assume. Okay.
Yes.
With that I already trained the data my model. Okay. It is seen already that data. Now if I again the next iteration again 30, what is the improvement it will do? Because the same.
Yeah. Yes. Okay. Good. So does anyone have a answer to that?
Yeah, I think so that basically when you're training for the first set mini batch and then you're updating for the last mini batch, so basically you're overriding the first mini batch's weights. So you need multiple iteration over same mini batch to come to an optimal solution.
Right. It's possible that by the end of in the first epoch, by the end of the starting mini batch to the last mini batch, or let's say from the starting sample to the last sample, it's possible that while doing the last few samples, it forgot what the first sample was, and it ended up classifying it wrongly.
No. I'm not telling I'm losing the weights. I'll keep that weight. But what the meaning of giving the same 30 samples once again to the model, which already seen that? No.
No, weights are lost. Weights are
say
overridden.
No. What my understanding?
Where will you keep the weights?
Yeah. See, when I come to the second epoch, okay, second epoch, I have initial value with me now. Weights are there with me. Am I right? My weights are already there. Okay. With that, taking as initial data or whatever formula I want to do it, then I'll do the second sample. Okay. Otherwise, let us look into another way. Suppose I have only 30 sample data is there. Okay. Now I given the first iteration all the 30 samples. I got the weights now. Again, given the same 30 samples, well, whether the model will improve, how it can improve. If I give the same data, how you are improving, or you are trying different hypothesis every iteration.
Because
understanding that concept.
See, this W old is what is changing, right? Between the epochs, Satish. This is what is
No. Let us see, sir. I'll think it's only one epoch. You will think now one epoch, one iteration I'm trying.
In one epoch, okay.
So I have 30 samples in my hand.
Okay.
So I given all the 30 sample to the model with the back propagation and all. I am now have one model with me. Correct. Now can I improve that model simply going one more epoch with the same set of data?
Yes.
Yes.
Satish sir, data remains same, sample remains same, but your weight keeps changing.
Right.
No, that's not my question. If I change if I'm giving the same data for the same neural network again and again, is it's improving? How it will improve? I'm not understanding because the data is same. No, anybody is learning from the data basically. Now data is same.
Yes, sir. Data may be the same, but model is changing. Model means the weights are changing, right? In each
is
epoch.
that in second epoch we change the sequence of same data?
See, if we don't change anything.
Changing with it.
Okay, so one thing I'll try to point out. Yes, what we generally do is we shuffle the data after this. That's not necessary.
Yeah.
That is a heuristic. I mean, again, that is something that people do generally because it works very well. That is fine. But the point being, it doesn't mean that it doesn't mean that this approach is wrong. No.
Sir, okay, I understand now different way. Okay, I understand your point now. Okay, I got the point now. What you want to say, basically, now I got after going for complete one iteration, I have the 30 samples now. Now after going the complete 30 samples, I have now weights. Now going that same the first sample again, I'm going now. Now my weights are already there, so it can learn much more better because this is I understand now point. Because when I'm learning the first sample, I don't have any back data at all. So seeing the first sample with some information, we can improve my model again. I understood the point.
Yes.
Clear what I'm saying? Yeah. I understood. See, for example, when I given the come for the model first sample, it doesn't have any history. It doesn't know anything.
Correct.
But at the same time, second time it's coming, has some history. It has some knowledge now.
Once
so it can, yeah. Now it can learn much better.
Much better.
So second time again coming, I have much more information about my data. Now the first sample it's learning much more better way.
Yes.
Okay.
Yes.
Now my question, how many iteration it will be learned? That is like heuristic method only then.
Yes.
How much?
how many times you have to run this epoch, this E, maximum value of E. Nobody knows, nobody can fix it. So usually what you do is you just try it for a long, like a large value, and then you use things like, for example, because you also have validation set with you. So you'll keep on testing on, you'll keep on getting a validation error. And the point where the validation error, starts increasing, the model has overfit. So there's no point training it anymore. So you at least stop the training at that point. You keep the maximum value of the repo, you keep it to a large value, like 1,000 or something.
Okay. Or in general, I'll break the loop when I reach my error resolution, whatever I want. In general.
Yeah. So we also have that approach where we say, okay, I'll have a thing on, let's say, how much have the weights shifted in the last update. So those things also people do, and then how much is the error changed, or is it less than some threshold that I wanted? Those sort of things are there.
Okay.
Can you go to my question now? My question that slides.
Yes. All previous questions are answered, I hope. We'll go to this question. So this actually is no point. Okay. So 1 minute. Yeah. So we had delta and epsilon, right? Epsilon and delta. So yeah. So epsilon basically tells you how much approximate correct it should be.
Means is it accuracy? Same as accuracy.
Yes. Same as error actually. More
error. Yeah. Opposite of accuracy.
It is error, right? It is not probability of error.
Yeah, it's probability.
Probability of
it is error.
It is error.
No, error and
error percentage probability basically.
No. So, with in the slides they were drawn one circle and another something ellipsoid or something, and they shaded an area which was called error. Okay, this thing is called the error. Now my question is, this error could be, error is what? It is not a probability, it is an error.
No, it's a probability. You are finding out how many errors you have found out with respect to all the training samples. Percent means ratio of error to total number of training samples.
Ratio of the
errors divided by error plus
total.
Correct.
Okay. So error upon total number of training samples is what is epsilon?
Yeah. The bound on that is epsilon. Yes, correct.
And now the other one, does it mean that our training samples are not good enough to represent the real world data? Is it that what is this?
What is the meaning of delta?
Yeah, I want to ask that.
So delta tells you, what is the probability that you will find such an approximately correct model, given the data, given the hypothesis space, assumptions that whatever you have, all of that is handled according to this delta. That's what delta means according to me, at least.
And epsilon means the error.
Yes.
The percentage error.
Correct.
Sir, can you explain that equation? PR means probability, and inside P means what?
Probability.
It's probability only. It's also probability only. So see again. Okay. So we're talking mainly about a two-class classification setting. Okay. In that setting, this is the best way to understand this is. C said that all of this region should be positive. The outside should be negative. H is saying no, all of this should be positive. Remaining is negative. Now we want to find a H which matches C the best, right? So the error of H, this what is one way that we can say how wrong H is using this error region. That is wherever C and H don't match, right? That is XOR condition, the XOR region that we have. So we're saying what is the probability of this region happening for a given H? That's what this means. Are we clear?
That is given by eta. Now another, what is the outside one? I'm not very clear. Means.
Okay. So
delta is confidence parameter, sir.
Yeah, right. Confidence parameter, but what is it? Practical.
Okay. So 1 second. So okay. So do we understand this equation at least, everybody? Is this clear?
Yeah, so this is the error, which is the samples which are mismatched upon the total number of samples.
Yes, correct. Yes. So
okay,
how much, or it tells how wrong H is, right? Now, this is so we call it approximately correct. Now, delta tells you what is the probability of finding this such a H. Now, so where does probability kick in here? That's one question, right?
Yeah,
Because
again, probability, how is it because there is delta between training data set and the real life data, or something? How is this probability coming into picture? Means uh, H, if I take, it's the entire set, means all the hypothesis space. What, why is again probability coming into picture? Means probability, and then again inside me another probability. So basically, it's probability of probability. So
yes. So see, we already have an we already we choose a hypothesis class, right? Capital H. Now, in this capital H, what is the probability that I will find a H, small h, such that it is approximately correct? That is the probability.
So we will, won't we be iterating over all small h within h?
Yes. Yes.
So we'll be choosing the best one, right, during training.
Yes. So
what's the probability about it's one? It's one, or is it like because of biases you're telling that we'll the if we are iterating across all small h within h and trying to find the most optimal one, then since we are iterating across all small h's, then the probability is one, right? Why again delta, that sorry, f's, what is that? Why
No,
again such?
but in practice, it is practically impossible to iterate through all possible hypotheses, right?
So my
That's why we
question
arrive
was,
at a
that is it, like is it because of bias that we are not doing that?
Yes. So one is inductive bias, right? I mean, the basically the choosing of H, capital H, right? This is one. Second thing is this probability we want over the approximately correct we want over all data,
All
which you
data.
don't even have. Yes, yes. Not just sample, your training sample, over all possible data.
That means test plus training data.
Test plus training. Yes, exactly.
Training,
Test plus
or
training. So
even
exactly. This is what we talk about here. No.
is
So
it only test data or outside, even after means any, we can increase the test, means after using some test data, after that when we generalize, is it during generalization that probability is coming? My question was that. So if we have 100 samples, we have divided 20 for test and 80 for training. So is this extra probability, the next probability is coming from, because the in real world such, maybe there may be 1 million data, but we have only taken 100 million to train and test. So is it because it's about the applicability of that small optimal small age that is found during the training, whether it's can be generalized to the other than this 100 data that we use during training and test? Is it because of that? Means uh, as in
I got your point, Abhirup. Yes. So when you said when you have 100 and you said okay 80 and 20, let's say you did training and testing, right? Now training at the end you're training with 80 examples. Now so this probability whatever you calculate, this delta that you want to find, it applies to even these 20 and whatever else exists in the universe.
and it does that the e symbol, what is that
Yes.
epsilon, is it only referring during training set, this epsilon? Not
So I think that's what it is, because see at the end because we don't
no, don't
wait
think.
no, 1 second. um
See, we have
If
yet
it's
to form the hypothesis.
See, this is
Therefore, it
what
has to be during training set.
So this is what it is, right? So you want an H whose error is less than epsilon,
And
right?
this D is real world data. Okay, this D is real world, actual
Actual,
large scale data.
yes, the true data that exists in the universe, right?
Huh.
So yes, so this is on the universe, that is on the true data. So see, we are saying what we're saying. I have a sample which is a training sample. Can I generate? Can I find a hypothesis such that it will be epsilon approximately correct on whole data? And because I want such a because I want such a hypothesis, what is the probability that I will actually find such a hypothesis, right? In
So
this
if you
particular
don't find that hypothesis, then automatically this eta condition will not be sufficed. Means that uh, E symbol, if it is 0.1, say in our case, if we take it as 0.1, if we don't get a proper small h, optimal small h via training, then if we apply it to the real world data, obviously that eta condition, 0.1 condition will not be sufficed. So why is again probability coming into picture? Means that eta should means incorporate that means
so you're saying
Yeah,
it
I
should
think
incorporate the
this
fact that
concept
we
of
might need more data. Is that correct?
come again.
Epsilon has to incorporate the fact that we might need more data.
Epsilon epsilon means the e.
Let's call it E, man. No epsilon.
Yeah,
It is E.
e.
Go.
Okay, so I meant uh, so basically I am not getting why two probability. One probability is already like correctness of the, means basically accuracy. E means inverse of accuracy, 1 minus accuracy.
Correct.
So this is we find out during means training, we find a optimal age. Now if with that model, that is that optimal age, when we apply it to test data, we will get another accuracy, say, and it may be less or more than the target E.
Right.
Okay, so but what is, I'm not getting this
Can I share
another
my
probability.
understanding, sir?
Can I
Sure.
just come in?
Go ahead. Who was
Yeah. So what I understood from this is like probability of approximately correct means first P is like, let's imagine we are trying to build this model. So we'll be running around like 1000 training samples. So probability of approximately correct is it what is the error we are getting from there. So now
Okay.
that is what is E. Then later on might be we will kind of use this model to predict it. Like let's imagine we will use this model for the next year to predict like over 200 times in different real world examples. So when you run that model 200 times, how many times is the error lesser than like 0.1? So what is that probability that this probability of error will satisfy? So that is what is accuracy. So accuracy is 90% of the time whenever you run, it will give you the error lesser than 0.1. So that is what at least I understood.
Yeah, I think that
yeah,
is
that
correct.
is mathematically it's coming to be that, but uh, basically she's meaning when we are iterating across the world data with that model which we found out, she's telling that 0.1 will be sufficed how with how much probability, say we ran 200 times across real world data, how many times for those set of data this model is holding good with that 0.1 condition.
Right. So it is 90% of the times it is accurate. So that is what it says. Like might be 90 means if we run in 200, like 100 times, 90 times it is accurate. 90
Yeah,
times it
yeah.
is
I
error.
also had that feeling. I also had that feeling because how many times we are actually running that model on real data, what is the probability of that condition of E being met?
Okay. Okay,
I
so
don't know. I'm not sure. That's why I asked the question.
one second.
Yes, sir. Yes, sir. As I understand it, this is related to sample complexity. This fact. So
We'll come to that. Just a minute. Just a minute. We'll come to sample complexity. Just a minute. So let's say, Avirup, let me give you this example. So we discussed about the XOR problem, right? Plus XOR X and plus, right? And let's say my hypothesis class is linear uh, equations, linear functions only, right? Now, if I ask you what is the probability that I will find um, a linear function which will give me, let's say, point one error only, with the probability that with maximum probability 1 minus delta, what will your answer be?
Linear is always 0, means error will be 1.
Right. So therefore, the probability that you will find such a h means which has, let's say, 0.1 error only in this capital H is 0. So therefore, this capital H may not be a good thing to try.
Yeah, it's coming, it's tending towards the same thing actually. Basically, during our training, because of bias or whatever be the training data set, we are not actually getting the optimal H-opt. H-opt. Correct. H-opt. So it's maybe because of bias we use during training, or else our training data set wasn't approximating the world training data set.
Yeah.
It's because of that probability this second probability is coming.
Is
basically.
coming. Yes.
Correct.
Yes. And as you mentioned, the point of number of points not being capturing the true model enough, which is also relates to Gopal Krishna's point, right? Sample complexity. Now, just because of the fact that you have something which is linearly separable, let's say, doesn't mean that it will do well on the whole data. That is because of the fact that you don't have, let's say, enough samples to learn from it. So hence that point that M thing comes into picture, M greater than whatever. So hence that's the Gopal Krishna's point. So you need enough data also.
Yeah, I have one small question. It will be solved easily. VC dimension of oriented lines, that is straight lines, in 2D is 3, she said.
In 2D is 3.
3.
Yeah.
VC dimension of H consisting of oriented lines, straight lines. H is basically straight lines. In 2D, VC is 3. So like she did many things, but if we do like, if there are 3 points in 2D, 3 points in a straight line, just draw 3 points in a straight line. But it's a 2D space, okay? Say in x-axis. Now, how is like how can we separate with a single straight line?
We cannot. Okay, so what now?
So how is VC3 then?
You tell me, how is VC3? Who wants to try this question?
Sir, I can share this.
Go ahead.
So VC3 is like, it is not necessary that this condition should satisfy for all subsets of 3. So for any one subset of 3, if it is means any one type of configuration of 3, if it satisfies, then that rule is applicable. That for VC3 it is satisfies.
Okay. So basically, highest number of samples where if it's for one of the set, if it satisfied, we will take that, and the next number of higher samples where it does not satisfy any of them, we will stop at that position.
Correct. Yes.
Okay, so basically to find means summarize, it's like highest possible samples we'll take in that dimension, and if we are able to do that segregation using the hypothesis space, whatever be it, then that we have to keep iterating with more samples over that, correct, till we reach a point where we to that point of samples in that same dimensional space, that where we cannot at all find a separable case, basically.
Yes, correct.
Okay.
But sir, I understood VC dimension, but I couldn't understand what does that VC dimension really convey. So that is what, because if I say VC dimension is 3, means what does it convey actually is, what is the use case, means what is the kind of implication of that VC dimension is
It's
not.
just for your M calculation, for your when your hypothesis space is infinite, there is basically mathematically it has been shown that we need to, if we know the VC, we'll be able to know the minimum number of samples that will be required to ensure that that condition which ma'am said, I forgot.
So, see, at least the way I understand, and like I've not had a formal education, education on this, but the way I understand is basically VC dimension tells you how many such instances will you be. What is the number of instances that you will be able to classify using this particular hypothesis space? Now, when I say VC dimension of this 2D space, this 2D space is 3, for example, it's telling you if you give me 3 samples, I will be able to classify it. Not surely, but maximum only 3 I can do. At max. That's the problem. So hence that point there came in, right? In that in the derivation. So VC of H is less than log, mod of H has to be greater than 2 power M, and then VC of H has to be less than log mod H base 2, those sort of things. So it's telling you what is the complexity that this particular hypothesis space can capture at the end of the day. This is what I understand.
I have a question. Like in 2D space, if we make say 4 points, okay, 4 points. So, like in a linear point, plus plus plus, say, and another say, yeah, any straight line pe just do plus plus plus, and upper pe no, yeah, minus. Now this is also separable by linear line. Then VC wise and not 4 for the previous case.
No. See, okay. So what it means is, let's say I have a 4 points, 1, 2, 3, and 4, right? Now, for this particular instance, all possible labelings you should be able to classify using a linear line. Let's say we were talking about H is 2D line in 2D space, right? Now, there is one use case. There is one case, right, where if I keep it plus minus, I cannot do. Therefore, this example tells you that it may not be 4. We don't know still. We don't know.
What is 3? Then 3 also same thing.
But I found up 3 points, right? 3 points I found in this 2D space where any possible labeling that I give can be solved using a straight line.
Bhushan, can you?
Who is this? Can you please unmute only if you have to ask anything?
So no, it's contradicting. I felt. Now go back. In this, you're saying this doesn't work. Then 4 pay. If we can find like this 4 points also where it will work, means.
No, I can share my point here, Abhirup. So I think what sir was saying is, for this 3, the pattern is important when subset. So for this pattern, triangle pattern, plus minus, you give any plus minus in any of for the 3 points, it will that straight line will be able to classify. So you
all
have to
possible
one pattern, yeah.
With for some fixed pattern, okay.
Exactly.
Yes, for one x, all possible labelings of that x, if I'm able to classify using this hypothesis space, then the VC dimension is, I think, greater than or equal to. Yeah, greater than or equal to this.
In 4 also can be done in same way. If you just do a quadrilateral. Just do quadrilateral ka vertices point. Okay. Now. Okay. It will not be able to do. It will not be able to do.
Yeah, XOR problem. Exactly, right? You won't be able to. That's
correct. Quadrilateral cannot be done. Okay. Fine. I got it. So basically, it's like for let me tell you if it's correct or not. Like if we say the same problem, basically in a particular dimensional space, we will keep increasing the number of vertices, means points. Okay, till we and we will, for those number of points, we will try to find one pattern for which we can segregate everything properly, means all conditions, means for example for 4 points for quadrilateral or linear line, if you are able to, for that particular pattern, if you are able to segregate plus minus properly, then we will go to the next step, next number of points, means instead of 4 we will try 5. If I don't find any patterns wherein one full pattern can be segregated properly with this plus minus, then 4 is our VC.
Yes.
So it's basically two iterations, vertices and then patterns.
Yes.
Vertices, two loops basically. Is number of vertices, that is number of points. Inner loop is pattern, and if one pattern is completely segregable, separable, then this condition is holding good basically.
Yes.
And we will continue till the maximum vertices for which one such pattern is holding good basically.
Yes, correct.
Okay.
Sir, but why is VC dimension called greater than that number, sir? It should be lesser than, right? Like, because only for like example, for that straight line, 3 is the max. So we say VC dimension of that hypothesis, straight line hypothesis, is greater than or equal to 3. So why is that it's called greater than? Because it can't do anything more than 3, right? It can only do till 3, 2 and 3.
No, think about this space, no? So let's say I have 2, and I have the same hypothesis class. H belongs to lines on 2D plane, right? So now if I take, so now the VC dimension is going to be what? It's going to be greater than or equal to 2, right? It's because 2 points, it will classify all possible patterns. I can take like this, I can take up, down, whatever, right?
Right.
So it means that there is it's possible that this particular hypothesis space may be able to do something better than the current one, and there's a place where it will not be able to do. That's what we'll consider as the endpoint.
But means to that understanding, it should be lesser than, right, sir? Because so if that straight line can do for max 3 points, it can do better, but for 4 points, it cannot do. So then it should be called lesser than 3, right? Why greater than 3?
No. Okay. So same question. Now let's say I'll give you the same H. Let's say lines in 2D plane, and I will tell you use 2 points. Now, will you tell me the VC of H is 2, or will you tell me VC of H is 3? But we already know VC of H is 3, right? It's not 2.
Right.
Okay. So based upon if I use, it'll be VC of H less than or equal to 2.
No, sir, but VC of H is 3, but it is not equal to 4 also, right, sir? But we have to say it can be, I should be saying lesser than 3, like not.
No. Okay, so fine. There are two things here. See, the point is when you do, let me just remove these.
Because what I'm saying is, if it is greater than, means it is satisfying 4 also, but 4 it doesn't work only, right? So that is what I was little confused there.
No, so VC of H becomes, so VC of H is less than or equal to 3 because of this condition. And then when you try on 4, you will get VC of H less than 4. Sorry, greater than or equal to 3, and you'll get VC of H less than 4. Now, the only value that can solve VC of H, these two conditions, is what? VC of H equal to 3.
Oh, okay. So it will have both the conditions, greater than or equal to 3 and lesser than 4.
And it is lesser than 4 because any pattern in this, so you couldn't find any such any 4 points arranged in any pattern for which any of the possible labelings could be solved by this H hypothesis space, right? So hence it is less than 4. Now therefore the VC of H turns out to be 3.
So why is they defining it in two equations, sir? And I can just say VC of H less than 4. Less than 4 means maximum 3 it can. So that is why VC of H can be 3. Why are they giving two equations to explain one simple point of VC of H equal to 3?
No. So okay, VC of H is now 3. So if I tell you VC of H, so that VC of H is also less than 10, no?
VC of H is less than 10. Yes.
10 also. So where do I know what is the best bound that you can get?
That is why they can say VC of H less than 4. So then I can understand maximum 3 it can satisfy. So only one equation, VC of H less than 4 will work, right?
See, so the point is like, see, it's like saying, okay, something is not existing doesn't mean it's the evidence of its absence. That's what in that way you should think about, if I'm not wrong. So VC of H less than 4 is right, but you also need to prove that VC of H is greater than or equal to 3. Because because it'll tell, okay, 3 points. Yes, I've checked for 3 points. 3 points it can classify. I've checked for 4 points. It cannot classify. Therefore, VC of H is 3. I mean, again, I would say yes. So your point is I can just say that what is the best lower bound that I have. So you can keep that and you can move ahead and see. It's what you will use also in your calculations, because when you do that sample size, that slide, right, where you had some m less than something, right? You had m less than VC of H, whatever. So there the point is you want an upper bound. So then you will use VC of H equal to, let's say, 4 or 3. You will get similar thing. But if you have the actual value, why not use it? This one.
Okay.
Yeah, but so the reasoning is this. It is greater than or equal to because it satisfies those values, less than because it doesn't satisfy any of the conditions, and therefore it comes out to be some number.
Okay.
That's the reasoning. Yeah.
Okay.
Okay. Anything else? Otherwise, we'll close the session. Oh God. Yeah. Okay. Anything else?
Sir.
Go ahead.
Yeah. I don't have any question. This is in general one request. Now next week we have the last session. Okay.
Yes.
Next Saturday. So suppose I asked last previous one TA also. Suppose we want to now ask some questions, because now we'll go through before exam. We'll go through all the slides and we'll revise it. Correct? No. So is it possible to make one session, because next week obviously will be questions on clustering and all things will be there. So we will not get an opportunities to ask our in general questions when we go revise it. So is it possible for you to take a session after that next Saturday, then one more on Sunday or Monday or any day? Sure. It's possible.
Sure. Yeah. So I actually wanted to ask that today. Like, what do you guys want or not? So okay. So next, that is 16th September. So we will solve the assignment 7 questions, right? And we'll focus on clustering, because that will be your assignment 8 that will come up in the next Wednesday. So September 23rd, we can have an additional session. So where any doubts regarding the whole course, we can answer, and we'll also solve the assignment 8 questions then, right? The clustering questions will solve that.
Sir, 23rd is too late, no, sir. 24 is the exam for us, correct, no?
Oh, so okay, so let me talk to NPTEL guys, because they handle the schedule in some sense. So we can do either on Friday or Thursday.
Yeah. One in between weekdays, no, sir. It will keep, no, or for other people also, because somebody told working people they are not easy. I don't know. So considering other people what timings they want, but I think it will benefit for everybody to keep it one week middle. That means I mean the 16 to 23, that date. 16 is the Sunday, somewhere will come till 23. Between that week, no, if you keep any on weekdays evening.
See. But my point is, see, 20th is your week 8 assignment submission, right?
Sir, 1 minute, sir. 16 is the next Saturday.
16 is next Saturday, correct?
Yes. Then after 23 is almost late, because 24th our exam will be there.
No. So okay, can you guys confirm 20th September will be the week 8 assignment date?
Yes, sir, that is correct. Yeah.
Correct. Yes. So what I'm thinking is either on 21st or 22nd or 23rd. These 3 days are there where we can discuss the assignment 8 solutions also, right? Because I mean, you might also in that also.
Okay. Yeah.
and I cannot discuss solutions before the deadline.
So I think that, yeah, I understand.
So yeah, so we can do 21st, 22nd, or 23rd. So any day is fine for me. That's not a problem.
I think 21st is better because we'll get enough. By the time we solved also, so even next day evening is, I think, better. I'm just thinking. Others can also tell their comments.
Yeah, that is okay, sir. Yeah, Thursday also should work for us.
Fine. So 21st September, 4 to 6. Does that make sense?
Yes, sir.
Same. We'll keep the timing same because it will be.
Yes, sir.
Yeah.
4 to 6 is other working.
I think 4 to 6 for working people, it will be little tough, sir. Might be little 5 or 5.
After 6 o'clock. Yeah, after 6 o'clock.
Yeah, after 6 is also 6 to 8.
6 to 8 is fine.
Yes, sir.
Yes, sir. I think 6 to 8 is fine for everyone, I think.
And the link will be shared in the same website, no, sir? The link. The link for the meeting should be in the same. The link for the meeting.
We'll use the same link. Link will be the same.
Sir.
We'll meet on this time. Yeah.
And is it so that session is Thursday 6 to 8 is okay, but is it possible to have one additional session, sir, before 20th? At least to see from first if we revise, might be we will not talk about assignment 8, but
yeah, some revision kind of things.
Some revision, because in case.
So
what happens is, sir, because on Thursday, if we discuss week 8, if in case many have more questions on week 8, we will engage most of our time on assignment 8. So we will not get our chance to ask from first to the rest of the thing.
Right. So so we also have the different TAs also, no? So even they'll have a session, right, on 18th and 19th. Won't they have?
Yeah, that's on Mondays and Tuesdays we have.
Correct. So in that session, so in those sessions you can do your general questions also additionally. Does that make sense?
Okay, understood. Got it, sir.
Yeah. Okay. So 18, 19. See, you'll anyway have the other TA sessions anyway going on, right? And then 21st we can do the clustering assignment solutions and general questions also.
Okay, sir. So we will get an announcement, right, sir, about this change in timing of the 21st.
Yes. So I'll talk to the NPTEL guys. Okay, and whatever it is, you will get an announcement. I'll also put it on the discussion forum just to be sure.
Sir, and one more question, sir. I kind of messaged regarding some issues or incorrect questions for assignment 3 and 4, sir. So we were waiting for that.
Yes. So it's going on. It'll take some time. It's going on. It's in the process. Okay. So I remember assignment 3 one question was there. Assignment 4 one question was there.
Right.
Assignment 5 we had a couple of questions. So 2 of them are already the discussion is over. We need to get it out on the portal. And 2 questions also. 2 questions we are still discussing. And that's it. This week we don't have anything like that. So yeah, so these 4 questions, it's going on. It'll take some time. It takes time.
Okay, sir. No problem.
Okay.
Thank you, sir.
Thank you.
Okay, guys. See you next Saturday. Chalo, bye.